Hello and welcome back to Probability and Statistics. In this video, we will discuss Bayesian statistics. Our learning goals is to know the basics of Bayesian statistics, be able to apply Bayes' theorem to compute probabilities, and be able to use a Bayesian update to compute probabilities. In this topic, we will discuss how the Bayes rule is applied to calculating conditional probability, and several real-life examples are demonstrated. Let's consider the table. It shows the result of a poll among 1,738 adult Americans. This table allows us to calculate probabilities. So here we have the adult Americans who used online dating site, and on the third column we have the adult Americans who did not use online dating site. We also have in the second column the adult Americans ranging from 18 to 29 years old. The third column is 30 to 49 years old. The fourth column is 50 to 64 years old. On the fifth column, we have 65 plus years old. And then the last is the total. Okay. So let's say, for instance, the probability of an adult American using an online dating site can be calculated as the probability of using an online dating site is equals to the number that indicated they are using an online dating site over the total number of people in the poll. So if we look at the table, so we'll get the total number that indicated that they use an online dating site. So here we have the second column, the total is 225 here. So we'll put that here. And then over the total number of people in the poll. So the total number of people in the poll is 1,738. So we'll put that here. So 225 divided by 1738 is equals to 13%. So that's how we compute for probabilities. So another is, this is the overall probability of using an online dating site. Say we are now interested in the probability of using an online dating site if one falls in the age group of 30 to 49. Similar to above, we have, so the probability using an online dating site given that in an age group of 30 to 49. So that will be equal to the number of age group 30 to 49 that indicated they use an online dating site. So over the total number in age group 30 to 49. So as you can see here on the second row, we have the adult Americans who used online dating site. So what we're going to need to do is get only the age group who uses online dating site. So 30 to 49, this is, so a total of 86. So we'll get 86 and put it here. So, and over the total number in age group of 30 to 49. So since the total number of people in age group 30 to 49 is 512, so we will put here 512 also. So 86 over 512 is equals to 17%. So we can rewrite this conditional probability in terms of regular probabilities by dividing both numerator and denominator by the total number of people in the poll. That is, so let's say, for instance, the probability of using an online dating site given in an age group of 30 to 49, so which is equals to number in age group 30 to 49 that indicated they use an online dating site over the total number in age group 30 to 49. That would be equal to number in age group 30 to 49 that indicated they use an online dating site over the total number of people in the poll over the total number in age group 30 to 49 over the total number of people in the poll. So the probability of using an online dating site given falling in age group of 30 to 49 over the probability of falling in age group 30 to 49. Okay? So here we have the Bayes rule. So the conditional when I say Bayes rule, this is the conditional probability of the event A conditional on event B is given by, so here's the formula of the Bayes rule or the Bayes theorem. We have the probability of A given B is equals to the probability of A and B over the probability of B. So what is the probability that an 18 to 29-year-old from the table uses online dating site? So here we have the previous formula, and we'll get the values. So the number in age group 18 to 29 that indicated the use online dating site is, I think, 60, and the total number of in age group 18 to 29 is 315. So that would give us a 19% probability of using an online dating site in age given that in age group of 18 to 29. So we come now to Bayes rules and diagnostic testing. So I will give an example. So here is an example of a scenario. So to better understand the conditional probabilities and their importance, let's consider an example involving the human immunodeficiency virus or HIV in early 1980s. So HIV had just been discovered and was rapidly expanding. There was major concern with the safety of the blood supply. Also, virtually no cure existed, making an HIV diagnosis basically a death sentence, in addition to the stigma that was attached to the disease. So here we have a situation which is a false positive when it is a test returns positive while the truth is negative. So that's why we call that false positive. That would, for instance, be that someone without HIV is wrongly diagnosed with HIV. So wrongly telling that person they are going to die and casting the stigma on them. We also have false negative. This is when a test returns negative while the truth is positive. That is when someone with HIV undergoes an HIV test which wrongly comes back negative. The latter poses a threat to the blood supply if the person is about to donate blood. So the probability of a false positive if the truth is negative is called the false positive rate. Similarly, the false negative rate is the probability of false negative if the truth is positive. Note that both these rates are conditional probabilities. The false positive rate of an HIV test is the probability of positive result conditional on the person tested having no HIV. So the HIV test we consider is an enzyme-linked immunosorbent assay, or commonly known as ELISA. So we would like to know the probability that someone in early 1980s have HIV if ELISA tests positive. For this, we need the following information: ELISA true positive rate, or the 1 minus false negative rate, also referred to as sensitivity, recall, or probability of detection, is estimated as the probability of ELISA is positive given that the person tested has HIV is equals to 93% or 0.93. Its true negative rate, or 1 minus false positive rate, is also referred to as specificity, is estimated as probability of ELISA is negative given that the person tested has no HIV, which is equals to 99% or 0.99. So also relevant to our question is the prevalence of HIV in the overall population, which is estimated to be 1.48 out of every 1,000 American adults. We therefore assume that the probability of person tested has HIV is equals to 1.48 over 1,000, which is equals to 0.00148. Note that above numbers are estimate. For our purpose, however, we will treat them as if they were exact, okay? So our goal here is to compute the probability of HIV if ELISA is positive. That is the probability of person tested has HIV given that ELISA is positive. In none of the above numbers did we condition on the outcome of ELISA. Unfortunately, fortunately, Bayes rules allows is to use the above numbers to compute the probability we seek. So Bayes rule states that the probability of person tested has HIV given that Elisa is positive is equals to the probability of person tested has HIV and Elisa is positive over the probability of Elisa is positive. So this can be derived as follows. For someone to test positive and be HIV positive, that person first needs to be HIV positive and then secondly test positive. The probability of the first thing happening is probability of HIV positive is equals to 0.00148. So we already know that. The probability of then testing positive is the probability of Elisa is positive given that the person tested has HIV is equals to 0.93. So the true positive rate, this yields for the numerator. So here we have the probability of person tested has HIV and Elisa is positive is equals to probability of person tested has HIV multiplied by the probability Elisa is positive given that the person tested has HIV. So if we already know that the probability of person tested has HIV is equals to 0.00148, and the probability of Elisa is positive given that the person tested has HIV is 0.93. So if we multiply 0.00148 multiplied by 0.93, so we'll get 0.0013764. Okay, so later on we will use this number. So the first step in the above equation is implied by Bayes rules by multiplying the left and right hand sides of Bayes rule by the probability of P. We obtained the probability of A given B multiplied by the probability of B is equals to the probability of A and B. This was also introduced in the past lecture, so as you can recall, the Bayes theorem. So the denominator in the previous example can be expanded as probability that Elisa is positive is equals to the probability of person tested has HIV and Elisa is positive plus the probability of person tested has no HIV and Elisa is positive. Since we already know that the probability of person tested has HIV and Elisa is positive is 0.0013764 based on the previous computation. So here we have another. So the probability of person tested has no HIV and Elisa is positive. For now, we can say that it's 0.0099852, which if we get the result, we add the two probabilities, we will get 0.0113616. So now, where did we get this value? The value of probability of person tested has no HIV and Elisa is positive. So here it is. So we use this formula. So the probability of person tested has no HIV and Elisa is positive is equals to the probability of person tested has no HIV multiplied by the probability of Elisa is positive given that the person tested has no HIV. So here we can get this one. We can get the probability of person tested has no HIV by deducting the probability of person tested has HIV, since we already know that, so which is 0.00148, so we will deduct that to 1, so 1 minus 0.00148. So and here also the probability of Elisa is positive given that the person tested has no HIV is 1 minus the probability of Elisa is negative given that the person tested has no HIV. Since we already know this one, the probability of this one, so we can deduct that to 1, so 1 minus 0.99. So we can now get the probability of person tested has no HIV and Elisa is positive. So now, so you have 1 minus 0.00148 multiplied by 1 minus 0.99. That will be equal to 0.009982852, which is the value on the previous slide. Okay? So that's how we get this value. So putting this all together reveals that the probability of person tested has HIV given Elisa is positive is equals to the probability of person tested has HIV and Elisa is positive over the probability that Elisa is positive. So if we interchange the values now, so the probability of person tested has HIV given that Elisa is positive is equals to 0.0013764 divided by 0.0113616, which is equals to 0.12%. So even when the ELISA returns positive, the probability of having HIV is only 12%. An important reason why this number is so low is due to the prevalence of HIV. Before testing, one's probability of HIV was, we all know that it's 0.148 or 14%. So the positive test changes the probability dramatically, but it is still below 50%. That is it is more likely that one HIV negative rather than positive after one positive ELISA test. So questions like the one we just answered, or what is the probability of a disease if a test returns positive, are crucial to make medical diagnosis. Okay, so as we saw, just the true positive and the true negative rates of a test do not tell the full story, but also a disease's prevalence plays a role. Bayes rule is a tool to synthesize such numbers into a more useful probability having a disease after a result. So here, another example, what is the probability that someone who tests positive does not actually have HIV? Since we already know, on the previous example, we found out that someone who tests positive has a 0.12 probability of having HIV. That implies that the same person has a 1 minus 0.12 or 0.88 probability of not having HIV despite testing positive. Okay. Another example is if the individual is at a higher risk for having HIV than a randomly sampled person from the population considered, how, if at all, would you expect probability of person tested as HIV given that ELISA is positive to change? So the answer for this would be if the person has a priori a higher risk for HIV and test positive, then the probability of having HIV must be higher also than for someone not increased risk who also test positive. Therefore, the probability of person tested has HIV given that ELISA is positive is greater than 0.12, or where 0.12 comes from the previous example. So one can drive this mathematically by plugging in a larger number in the previous example than 0.00148, as the number represents the prior risk of HIV. Changing the calculations accordingly shows that the probability of person tested has HIV given that ELISA is positive is greater than 0.12. Okay? Another is if the false positive rate of the test is higher than 1%, how, if at all, would you expect that the probability of person tested has HIV given that ELISA is positive to change? If the false positive rate increases, so the probability of a wrong positive result also increases. So that means that a positive test result is more likely to be wrong and thus less indicative of HIV. Therefore, the probability of HIV after a positive ELISA goes down such that the probability of person tested as HIV given that ELISA is positive, it will be lesser to 0.12. Okay, so that would be. So let's come now to Bayesian updating. So to solve this problem, in the previous example, we saw that one positive ELISA test yields a probability of having HIV of 12%. Okay, so to obtain more convincing probability, one might want to do a second ELISA test after a first one comes up positive. So what is the probability of being HIV positive if also the second ELISA test comes back? Okay, so to solve this problem, we will assume that the correctness of this second test is not influenced by the first ELISA test. So that is, the tests are independent from each other. Okay, so this assumption probably does not hold true, as it is plausible that if the first test was false positive, it is more likely that the second will be one as well. Nonetheless, we stick with the independence assumption for simplicity. So in the last section, or in the last slide, um, we used person tested has HIV, or the probability of person tested has HIV is 0.00148. So to compute the probability of HIV after one positive test, so if we repeat those tests, those steps, but now with person tested has HIV is equals to 0.12%, the probability that the person with one positive test has HIV. So we exactly obtain the probability of HIV after two positive tests. So repeating the mask from the previous section or example involving Bayes rule gives us this formula. So, or this computation. So the probability of person tested has HIV given that the second ELISA is also positive is equals to the probability of person tested has HIV, which is 0.12 percent, or 0.12 or 12%, multiplied by the probability of second ELISA is positive given that the person has HIV, which is 0.93. Okay, so over the probability of second ELISA is also positive, which is equal to the probability of person tested as HIV multiplied by the probability of second ELISA is positive and has HIV, plus the probability of person tested has no HIV, and multiplied by the probability of second ELISA is positive and has no HIV, which is equal to, we have the value now. So in the previous example, it's 0.12, the probability of person tested has HIV, multiplied by the probability of second ELISA is positive and has HIV, which is 0.93, plus 1 minus 0.12 and multiplied by 1 minus 0.99. Okay, so if we compute that, we will get 0.93. Okay, so here is a graphical representation of Bayesian updating. So as you can see here, this is our first Bayesian computation. So we have 0.12 and no HIV is 0.88, as we can recall in the previous example. So if we run another series of Bayesian updating, we could get that the probability of the second ELISA test is 0.93. Okay, so in no HIV, it's 0.088. Okay, so that's how we um, conduct Bayesian updating using tree. Okay, so as you can see here. So this process of using Bayes rule to update probability based on an event affecting it is called Bayes updating. More generally, the what one tries to update can be considered prior information, sometimes simply called as the prior. The event providing information about this can also be data. Then updating this prior using Bayes rules gives the information conditional on the data, also known as the posterior. As in the information after having seen the data going from the prior to the posterior is Bayes updating. So the probability of HIV after one positive ELISA, which is 0.12, was the posterior in the previous section or in the previous slide, as it was an update of the overall prevalence of HIV. However, here we answered a question where we used this posterior information as the prior. So this process of using posterior as prior in a new problem is natural in the Bayesian framework of updating knowledge, information as the prior. This process of using a posterior as prior in new problem is natural in the Bayesian framework of updating knowledge based on data. So here we have another example of Bayesian updating. So what is the probability that one actually has HIV after testing positive 3 times on the ELISA? Again, assume that all 3 ELISAs are independent. So again, we can use the Bayes rule or the Bayes updating in updating the Bayes rule. So probability of person tested has HIV given that the third ELISA is also positive. So if we follow, so as you can see here, we have 0.93 multiplied by 0.93 over 0.93 times 0.93 plus 1 minus 0.93 multiplied by 1 minus 99 is equals to 0.999. So the probability of person tested has HIV given that the third ELISA is also positive is 0.999. Okay? So that's it for Bayesian statistics. So if you have any question, you can raise it on our group chat. So thank you very much and stay safe.